Cornstarch packing peanuts. Evolution from expanded polystyrene to sustainable loose-fill packaging materials. The rapid growth of e-commerce has significantly increased the demand for protective packaging materials that prevent damage during shipping, while minimizing environmental impacts. Among loose-fill cushioning materials, expanded polystyrene, EPS, packing peanuts have dominated the packaging industry since the 1960s due to their lightweight nature, excellent shock absorption, and low production cost. However, their persistence in the environment, poor recyclability, and dependence on petroleum feedstocks have driven the search for sustainable alternatives. Cornstarch packing peanuts, manufactured primarily from thermoplastic starch, TPS, have emerged as one of the most successful biodegradable replacements, combining renewable raw materials with environmentally friendly, end-of-life characteristics. This video summarizes the historical development of packing peanuts, the transition from EPS to starch-based materials, manufacturing processes, material properties, advantages, and remaining technical challenges. Historical development of packing peanuts. The evolution of packing peanuts is closely linked to the invention of expanded polystyrene. Polystyrene was first synthesized in the 19th century, while its commercial significance emerged during the 20th century. A major milestone occurred in 1941, when Dow chemical scientist Ray McIntyre accidentally developed extruded polystyrene foam while investigating lightweight insulating materials. Commercialized as styrofoam, this closed-cell foam rapidly gained popularity in construction, insulation, and packaging applications because of its low density and excellent mechanical performance. Loose-fill packing peanuts were introduced commercially during the mid-1960s, with their characteristic peanut-shaped geometry designed to interlock during compression while easily flowing around irregularly shaped objects. This geometry enables efficient void filling, impact absorption, and protection of fragile goods during transportation. Throughout the 1970s and 1980s, EPS packing peanuts became the industry standard due to their excellent cushioning efficiency, dimensional stability, moisture resistance, and inexpensive manufacturing. Despite these advantages, increasing concern over plastic pollution and landfill accumulation highlighted the environmental shortcomings of EPS. The material is derived entirely from fossil resources, degrades extremely slowly, and fragments into persistent microplastics. Recycling is economically challenging because of its low bulk density and contamination during collection. Consequently, governments and environmental organizations began promoting biodegradable packaging materials, leading to the commercial introduction of starch-based packing peanuts during the early 1990s. Evolution to cornstarch packing peanuts. Growing environmental awareness stimulated research into renewable polymers capable of replacing petroleum-derived plastics. Starch became an attractive candidate because it is inexpensive, abundant, biodegradable, compostable, and produced from renewable crops such as corn, potatoes, wheat, cassava, and sorghum. Cornstarch rapidly became the dominant feedstock owing to its global availability and established processing infrastructure. Unlike synthetic polymers, cornstarch is a natural polysaccharide composed of glucose units organized into two distinct macromolecules, amylose and amylopectin. Amylose is a predominantly linear polymer connected by alpha-1,4 glycosidic bonds that contributes rigidity through its helical structure, whereas amylopectin is a highly branched polymer containing alpha-1,4 and alpha-1,6 linkages that provides flexibility and facilitates biodegradation. Typical cornstarch contains approximately 20 to 30% amylose and 70 to 80% amylopectin. and the balance between these components strongly influences the mechanical and processing characteristics of starch-based foams. Manufacturing of cornstarch packing peanuts. Native starch cannot be processed like conventional thermoplastics because its semi-crystalline granules do not soften upon heating. Therefore, starch is converted into thermoplastic starch, TPS, through gelatinization and plasticization. During gelatinization, starch granules are heated with water and plasticizers such as glycerol, disrupting hydrogen bonds within the granules. Amylose diffuses out of the granules, while amylopectin becomes increasingly amorphous, producing a processable thermoplastic material. Commercial production employs twin-screw extrusion, in which TPS is subjected to elevated temperature, pressure, and shear. As the molten material exits the extrusion die, rapid pressure release vaporizes residual moisture, producing a lightweight cellular foam similar to EPS. The resulting packing peanuts possess interconnected pores that provide excellent void filling and impact absorption, while remaining completely biodegradable. Properties and characteristics. The properties of cornstarch packing peanuts are governed by the molecular structure of TPS and the cellular morphology generated during extrusion foaming. Like EPS, TPS foams possess low density because of numerous gas-filled cells, although the pore size distribution is generally less uniform. These foams exhibit adequate compressive strength and energy absorption for protecting lightweight and moderately fragile products. An important advantage is their anti-static nature, making them suitable for packaging electronic components without generating electrostatic discharge. In addition, starch foams readily conform to irregular product geometries, efficiently filling empty spaces within shipping containers. The abundance of hydroxyl groups in starch leads to extensive hydrogen bonding, imparting relatively high stiffness, but also making the material highly hydrophilic. Consequently, cornstarch packing peanuts readily absorb moisture and dissolve upon prolonged exposure to water. Thermoplastic starch also undergoes retrogradation during storage, in which molecular rearrangement increases crystallinity and brittleness over time. Nevertheless, the glucose-based polymer backbone is readily degraded by microorganisms into carbon dioxide, water, and biomass under composting conditions, eliminating the long-term environmental persistence associated with EPS. Advantages and challenges. Cornstarch packing peanuts offer several significant environmental advantages over EPS. They are produced from renewable agricultural resources rather than petroleum, require lower fossil energy input during manufacturing, and generate fewer greenhouse gas emissions over their life cycle. Unlike EPS, they dissolve in water, produce no persistent microplastics, are fully compostable, and safely biodegrade under natural conditions. Their anti-static behavior also eliminates the need for chemical anti-static additives commonly used in conventional foam packaging. Despite these benefits, several challenges continue to limit broader commercial adoption. The greatest limitation is moisture sensitivity, as water absorption causes swelling, softening, and loss of mechanical integrity. Starch foams also exhibit lower dimensional stability and mechanical durability than EPS, particularly after prolonged storage due to retrogradation. Manufacturing costs remain relatively high because of agricultural feedstock variability and the need for specialized processing and plasticizers. In addition, the slightly higher density of TPS foams can increase transportation costs. Improving water resistance through polymer blending or chemical modification often reduces biodegradability, requiring careful optimization of material composition. Future perspectives. Current research aims to overcome the intrinsic limitations of thermoplastic starch through advanced materials engineering. Reinforcement with cellulose nanofibers, cellulose nanocrystals, nanoclays, graphene oxide, and lignin nanoparticles has demonstrated improvements in mechanical strength, moisture resistance, and dimensional stability, while maintaining biodegradability. Similarly, blending TPS with biodegradable polyesters, such as polylactic acid, PLA, polybutylene adipate coterephthalate, PBAT, and polycaprolactone, PCl, enhances toughness and water resistance. Other promising strategies include reactive extrusion, bio-based hydrophobic coatings, enzymatically modified starches, and environmentally friendly plasticizers. Life cycle assessment studies increasingly demonstrate that starch-based loose-fill materials possess substantially lower environmental impacts than EPS, supporting their growing adoption as sustainable packaging materials. In conclusion, cornstarch packing peanuts represent one of the most successful examples of replacing petroleum-derived plastics with renewable and biodegradable materials in the packaging industry. Produced from thermoplastic starch through extrusion foaming, they provide effective cushioning, anti-static behavior, compostability, and reduced environmental impact. Although challenges such as moisture sensitivity, retrogradation, and higher production costs remain, advances in biodegradable polymer blends, nanocomposite reinforcement, and green processing technologies are steadily improving their performance. As environmental regulations tighten and demand for sustainable packaging continues to grow, cornstarch packing peanuts are expected to play an increasingly important role in next-generation protective packaging systems.